Hello. All right, so we're gonna go through a little bit of the Alex reports, just one today, and then we're gonna do some catch-up problems on sig figs and uncertainty, and then we'll start talking about the beginnings of chapter 2, where we get into the periodic table and the atoms. So in the Alex report, it's showing the current module progress. And I had a question from a student, and I need to look into this. They said that after they passed the CHO1A and the review module, they could not get back into those. And so I need to see. I was under the understanding that you still had the deadline and you had to finish by the deadline, but that you could still work on material that you hadn't finished yet. So I need to see on that. And if that was you, I'm working on that. I just got the email this morning. So. But as far as the module that's due next Monday, the 01B, Chapter 1B, we've got some folks that are finished with that, a few, and some folks that have got quite a few of the topics taken care of. So these are percentage of topics in that set. So, some people are 40% through those topics. But there's quite a few folks that are still, like 22 folks that are still not have mastered any of those topics. So that doesn't mean they haven't worked on it yet. I was looking to see, have they logged in or whatever, and it's showing that they did work on it, and some of them have worked quite a lot on it. So if you go there and you can see that we're working on this bottom one, 14% have finished. But if you've been working on this homework set for, I would say, 3 hours and still aren't showing any topics added to your pie or haven't mastered any of those topics, go now to the ASC and start getting some support on the chemistry. Okay. Again, there's no shame in that. I'm just saying, don't think everything's going okay and that it's just Alex. People are making their way through Alex, and if you're banging your head against Alex and still haven't gotten past any of the topics, then let's get tutoring. Let's start now, because we're way ahead of the tests, way ahead of the things that are going to really harm your grade. Okay, so this is an indicator that you're going to need some extra support for the course. So again, I don't know who it is. It's anonymous, but I hope they're here. But if you're just really finding that you're not able to do any of the topics, then definitely get tutoring now. Okay, so let's look at some of the catch-up problems. A lot of folks, when they're talking about the significant figures, don't really understand what's the importance of those. It's all about uncertainty, okay? So what is this idea of a significant figure? Well, it's something that it has to deal with uncertainty. So if we're measuring this temperature with this thermometer, okay, and we look in there and we see the tick marks on the scale there, and we try to make a judgment as to where that is when it's between the tick marks, sincere scientists may produce different numbers, because there's an uncertain number in there too. We know that it's above 25, and we know that it's below 30. So we're very sure of that tens place. We know it's a 2, it's not a 3. So we're certain in that digit. It's the second digit, the ones place, that we're uncertain about. Okay. Now we're pretty sure it's above a 5, but we're pretty sure it's not a 9. Okay. So it's somewhere between 5 and 9. And that second digit of 27 is an estimate. And so you may estimate that as a slightly different one. Maybe you said it's 26, or maybe you think it's 28. Okay? Honest scientists are going to disagree on where that line is, because there's no tick mark. Okay? And so this, even with the best situation, repeated measurements will also differ by small amounts. And you could have bias in your system. Let's say we had a system, this thermometer had an air bubble in it right here. Okay, so let's say that's air. If you've got air down below, then the level of liquid is going to be too high. So that thermometer is going to be biased high. All the temperatures that it reads above that air bubble are going to be too high. Now, they can be read repeatedly, they put it in the sample and read it, so they may be very precise, but they're all going to be biased high. And so that's when we get into accuracy. That would be an inaccurate thermometer, but it could still be precise. So in Alex, you have problems like this, where it's mimicking you reading analog devices. So here's an example of one. It's a burette reading, and you zoom in, and you try to measure, or it's a graduated cylinder, you try to measure where the level of that liquid is. Now, this is a situation where we've got water and glass, and the water is wetting the glass, and so you've got a curved surface called a meniscus. And we have had to decide as scientists where to read this thing, because there's water up here and there's water down here and this whole sloping area. We've decided to pick the bottom of the meniscus here because it's horizontal and it's easiest to compare to the marks. That's really the only reason. Okay. Now we've adjusted this glassware to take that extra bit of water into account. So it's already been adjusted. And so the glassware was made for that type of reading. And so we've got to read it the same way that the manufacturers of the glassware have made their instruments to read. So they've taken into account this extra little bit of water here. So you don't have to worry about that. The marks on the glassware have taken that into account. So they're depending upon you reading it the same way that they made it. Okay, so that's why it's important. So if we look at this, we see that the labeled marks are 20 mils apart. We have a 60 and an 80 and 100 and so on. So the numbers are 20 apart. And so that means that middle mark, the big one, is 70 milliliters. So from 60 to 80, halfway is 70. And then there's another mark there, which means it's 75. It's halfway between 70 and 80. So the first thing to do when you're reading a piece of glassware, figure out what the marks mean. Okay? And then once you know what the marks are, then you can estimate. So the bottom of that meniscus is about a fifth of the way up between 75 and 80. So the reading would be 76 mils. Now this is a graduated cylinder, so it fills from the bottom. So the numbers go up. But a burette, the numbers get bigger as they go down because it's measuring how much liquid was delivered. So when you open a burette, the further it falls, the more liquid has been delivered to the flask below it. So that's why it starts out at 0 and goes down to, say, 50. And so you got to pay attention. Am I reading a burette where the numbers get bigger as it goes down, or am I reading a graduated cylinder where the numbers get bigger as it goes up? So it's just, you got to know what situation you're in and what kind of glassware you're using. And it'll be obvious. Just look at the numbers and you'll be able to see. Yes?
To me, it looks like 60 at the bottom, next line 65, next line 70.
Yeah, okay, I see what you're saying. This 60.
Look at 80, the 8's almost touching the.
Yeah, so this you can't see the 60 line. It's really right down here. Yeah, so it's on top of the big line. Very good. And honestly, it's because I was just trying to shorten the number of slides I had. So I could have made a slide with the normal view, and you would have seen the bigger marks. Yeah, so I zoomed in already. No, don't worry, you're not going crazy. And so yeah, it's the big marks are 20 apart, but you can't really see the bottom of that. So that's why the little bracket goes down to here. So, but it's a very subtle thing. So we're looking at that, and I don't know. I mean, I'm judging that as a fifth of the way up. So I'm looking between this mark and that mark, and I'm thinking, well, it's not halfway. It's less than halfway. I could have maybe said a quarter of the way and called it, this would be 75 and another quarter, so it would be 77 and a half or something like that, instead of 76. But that's getting into the third decimal place, or the third significant figure, and I can't really say. So I'm just going to add, 75, 6, 7, 8, 9, 10. Okay, and so it looks like it's 1/5 of the way. That's my best estimate. I put that into Alex, hit check. I got it right. Okay, so that's good. When I talked about that bubble in the thermometer, I was talking about bias that would change the accuracy. And that would be this middle situation. I've got good precision. I know how to read a thermometer, and I've got a good, thermometer, except for that bubble that's in there. So all my numbers are off by a set amount. So the readings are all tightly grouped together, but they're not on the actual value of the temperature. So that would be poor accuracy. If I have it right on the actual value of the temperature, that'd be good precision and good accuracy. And I think every scientist in the world uses a dartboard to talk about precision and accuracy, because precision is how frequently the dart's hit in the same spot. Those would be your measurements. You know, if I do the experiment 5 times and I get all very similar values, then I've got good precision. And then if they're the actual true value, so I have a standard to compare it to, then that would be the accuracy. Do I get the right answer? We got to know what the right answer is before we can calculate the accuracy. If I have poor accuracy and poor precision, then the readings are all over the place. Okay. So now let's talk about significant figures and math. So last time we had a little bit at the end of the lecture on significant figures and how to account for them in terms of whether there's got zeros at the end or in the middle or at the beginning and so on. So now we have the math. We got to follow this uncertainty if we do things like averaging, or we've got measurements that are subtracted. A lot of times in weighing things, we weigh out the container and then we put the substance in, and the balance just calculates the total mass. We've got to take a difference. So what do we do when we take those differences in terms of significant figures? So here's the way I do all of my addition and subtraction and keeping track of significant figures. So over here, the example is 17.87 minus 0.770. So I go ahead and do this the traditional way of taking a difference here. I've got the big line here. But then I look at the place value of the uncertain digits. So that 0.87 is uncertain in the hundredths value. The 0.770 is a little bit more precise. It's got a thousandths place value. But when I take this difference, I'm going to only round. I'm going to round to the hundredths value, because if I'm uncertain here, I'm crazy uncertain there. So I'm not even going to worry about that one. So it's all about uncertainty. So if I'm uncertainty at hundredths, there's no way I'm going to try to say anything about the thousandths. So I just eliminate it. The next one's even more dramatic. So the 6.820 grams minus half a gram, okay, gives us this result, but we're not done. We've got to round that at the tenths place. Because if I'm uncertain in tenths, don't ask me about thousandths, okay? So 6.3 grams would be what you would write. Are there any questions on this? Yes?
The first one, you don't take into account the first two, I'm thinking because of your -7 or 0.770, isn't that just 3 sig? Right?
It is 3 significant figures, yeah. But you don't take into account the number of significant figures when you're doing addition and subtraction. It's only place value. So it's just a different mindset. When you're doing addition and subtraction, you only think of the place value. So, yeah, it could, like this one only has 1 significant figure on the 0.5, okay? But in the end, we have 2, because we're just focusing on place value. What's the magnitude of my uncertainty? And in this case, it's in the tenths place, and so we're stuck.
Is that because we're starting by subtracting 0.5 and there's only 1 sig fig?
Yeah, well, it's the place value, tenths.
Right.
We're only talking about tenths.
Okay. So
Yeah.
So would it be? Could you say that you like in 17.87? Well, that's 4 sig, but we're only going to the hundredths because we
Yes.
start with a value
That is uncertain in the
in the
hundredths.
hundreds, and we're subtracting a value on
Yeah.
the one that's uncertain.
Right, so think about that graduated cylinder problem. We were very certain with all of the front digits, but that last one was an estimate.
Right.
Yeah.
Okay.
So in scientific measurements, that last value is the estimated value. That's what we mean by uncertain. It's the estimated value. So if I'm estimating at hundredths, I can't say anything about the thousandths. And if I'm estimating at tenths here, I can't say anything about hundredths. Yeah. So if you're doing an uncertainty analysis in the second situation, that 0.5 is killing you. So we'd go back into the lab and say, why do we only have a 0.5? We need more significant figures? Did you just round that in your notes? So it's also about communication. If you, let's say you measured it on the balance and it said 0.5000 on the balance, and you were lazy and left off those last 3 zeros, you've wrecked your experiment in terms of precision, because you're having to round off all this information just because you wrote it down in a lazy way. So it's a very important thing to pay attention to where the estimated digit is. Okay, now multiplication and division is where we count the number of significant figures. So here we have 279.09 moles divided by 0.59 liters. And so we do the math. It's calculating molarity here. And so if I type this into my calculator, I get all of these extra digits. Okay. The calculators don't make you more precise. They'll give you lots of information, but it's garbage. It's garbage information. So we've got to look at the significant figures here. So we have 5 significant figures on top and only 2 on the bottom. And the 2 is what's going to limit us. So our volume measurement in this case is going to limit us to, we could say 470, but that's ambiguous. So if we said 470, it looks like 3 significant figures. And that's where we need to use scientific notation, because how do we write 470 with only 2 significant figures? If I put a decimal place, I'm saying I'm certain in the zeros place. And so this is a real problem. So we just have to write this in scientific notation. Okay, so that's 4.7 times 10 to the 2 moles per liter. So this is what you would write because it has the 2 significant figures. So if you're doing an Alex, you're going to have to use that times 10 to the thing. There's a little template. You click on it and you got to put the 2 in for the template. All right, this bottom one is 7.81 times 0.525. And we get a calculator gives us lots of extra digits, but we have 3 significant figures in the 7.81, 3 in the 0.525. And so then the result needs to be rounded to 3 significant figures. So do I have one? Oh, that's okay. And I've like left some blank boxes in your notes so you can fill them in. If you feel like I'm not leaving enough blank boxes, or if I'm leaving too many blank boxes and you can't keep up, let me know. It's because it's a work in progress, and I'll take your feedback. If I can make it better, I want to make class better. Okay, let's do a combo. So just like we use the order of operations, if you've got a fraction and a subtraction and so on, you're probably going to do the subtraction first and then do the divide. We do the same thing with the significant figures. So we have this situation where we've got a subtraction and a division. We've got to use both situations that we just talked about. So just like you would do order of operations, you would subtract that first, and then you would type in the next number and divide it. We're going to do the subtraction first here. So 97.2 minus 7.500. We're going to round that to the 10th place. But here's where I want you to I'm going to introduce a new term. I haven't seen this in the book, okay? But this is what we do as scientists. We do what's called keep guard digits, okay? We write down that we have 3 significant figures, but we keep these zeros when we do the subtraction, okay? When we do the division, just so that we don't have rounding errors that get worse and worse throughout the problem. So we keep these guard digits all the way through to the end, and then we round at the end. But we keep track of the significant figures. So when I do the subtraction, I round to the 10th place, and now I have 3 significant figures. Is everybody okay with that step? Let me see if you nod if you're okay with that. Okay. So these extra 2 zeros are what I call guard digits. They're just keeping me from having rounding grow to a higher degree and cause problems at the end of the problem. So I'm gonna take that now, and I'm gonna divide this number by the 187.9, and I get this long thing in my calculator. And so I've got 3 significant figures divided by 5 significant figures, so I need to round the result to 3. And so it'd be 0.477 grams per mole. Okay. So that's, I just want to introduce this term. So when you're doing all of your math and so on, maybe you have a whole string of multiplications. You know that your result is three significant figures. We'll have three significant figures because some number in your huge problem has three significant figures. Go ahead and do all of the math without rounding, and then round at the end. Okay. Then we shift gears in Alex problems completely, and we start talking about properties of materials again and density. Okay. And I like this problem. It gets you thinking. Okay. So in this case, we've got a little balance. Got to kind of think about how a balance works. Whatever's heaviest will be lower. You know, it's a balance beam. And the needle's right in the middle. So it says both of these objects have the same mass. Can you get that, right? The needle's in the middle, they're balanced. Okay? And so that's one of the questions. Which object has the greater mass? Well, they're equal, so it says neither, they're the same. So you click that guy. And then you look at the next one. Which object has the greater volume? Well, just look at the pictures, right? All right, that's got the greater volume, clearly. Okay, and this is just getting your mind around the concept of density. Which one has the greater density? Well, the one that has the smaller volume but the same mass. Okay, so it's packed in a smaller place. So that's the idea of density. It's how much material is packed in a particular spot, a particular volume. And this is a property of all our different materials. This was, do you remember, was it Archimedes that discovered how to determine if the king's crown was gold or not? And so he was tasked with figuring out if the crown was fake or not, if it was fake gold or real gold. And he sat in his bathtub and he noticed that the level of the water went up when he got in the tub. And then he got out and went down. And he realized he could measure the volume of the crown using water displacement. He knew he could weigh the mass of the crown, but how to know if it's gold or not? And the mass in a particular volume is a property of materials. And so he could test iron and copper and brass and gold by this technique. Weigh them, put them into a bathtub, and he could test to see if that crown was gold or not. So he was excited and he yelled Eureka and ran down the street naked because he just was in the tub. So that's the Archimedes story. So it's about density, and density, you can definitely tell the difference between gold and brass. They're both shiny yellow metals. One's an alloy, brass is an alloy, not nearly as dense as gold. So good old Archimedes. Now we can use density to find the properties of other things like liquids. So here's an example of using some data to calculate the density. And this is in the problem. It's given a small amount of this liquid, which is an unknown liquid of 968 grams, and it's in a particularly small volume, 0.608 liters. So we can calculate the density. And again, it's got three significant figures because of the volume. And so we'll have three significant figures in the end. And then again, it's one of those situations where it's going to be hard to round to that number and keep track of the significant figures. So we'd want to write that in scientific notation. But also the data in the table is per cubic centimeter. So there's 1,000 cubic centimeters in a liter. And so when we convert that over to cubic centimeters, then we end up with 1.59. So that's our density for this particular liquid, this unknown liquid. And you could take that to a table of densities and you could compare it. And you see that in here, carbon tetrachloride is 1.6. So this is very close to 1.6. And so this unknown liquid on the shelf where the label has fallen off, you measure the density of it, you say, okay, that's carbon tetrachloride. Of these options, it's one of these 5 liquids. And so sure enough, down in Alex, you could type in your 1.59. And yes, you could identify it using that table, and yes, it's carbon tetrachloride. So I love these problems because in the past, I would have just asked the calculation, and you would have learned how to do the math, but you wouldn't have really seen how it's useful. And this is a great example of how you could use density in an actual lab, and it makes you think a little bit more. So I like that a lot. Any questions on these? We're going pretty fast. And I'll open it up at the end. We can do questions that have come up in your notes. Okay. All right, so that's really all that's going to be on the Monday's homework. We're going to start on looking ahead to the periodic table and the atoms and their properties. So there's some Alex problems called just reading a periodic table entry. Write the symbol for every chemical element that has the atomic number greater than 3 and an atomic mass less than 11.6 U. Okay, and they don't tell you what U is. Okay, so it stands for an atomic mass unit. Okay, and so you can look up here, you click on an atom, like I clicked on boron, and I get this entry. It says B, it's the elemental symbol and the name boron. It has atomic number 5, and then here it says atomic mass 10.806 Da. Well, how does that match U? So that's weird, okay? And then it's got a metalloid, a type of element, it's a metalloid, and electronegativity is 2. We haven't discovered what that is yet, okay? Not in this class. And so I don't even know how to use all this information. So I'm trying to tell you, I do, but I'm trying to tell you, I'm putting myself in your stance. The answer is B, E, and beryllium and boron. Okay, but why is that? Well, this is super important. The masses on the periodic table are given many different names. So you'll see the name Dalton. It was Dalton's law of atomic theory, or Dalton's atomic theory, that gave us this, reinvigorated notion of atoms. We'll talk about that later in the course. You might even see atomic mass unit, AMU, or U. So in the problem, it talks about U. That's the same as a Dalton. And the most useful for us when we're doing stoichiometry is grams per mole. So the masses on the periodic table are going to be the grams and grams per mole. So you can read them right off the table and use grams per mole. So all 4 of these are equal. So a Dalton, a U in these problems, or AMU, or grams per mole, those are going to all be the same. Okay. So essentially we're looking at this, it needs to have an atomic number greater than 3. Well, you can see that at the very top of these things, the atomic number. So hydrogen has an atomic number of 1, helium 2, lithium 3. So greater than 3 would start with beryllium. So beryllium is 4, boron is 5. Carbon is 6, and on and on. Okay. We start looking at the masses. We get to boron. It has a mass of 10.8. And this problem is asking for all of them that are less than 11. Okay. So if we go on to carbon, it's going to be 12. That's going to be greater than 11. So the only ones that fit this little Venn diagram that's given in this problem is beryllium and boron. And so you type in beryllium, boron, and to Alex, and you get the green check mark. But if you were confused by them putting U in the problem and then the periodic information being Dalton's, I get that, okay? And then later we're going to be pulling those numbers off and they're going to be grams per mole. This is the periodic table that you're going to get on your exams, okay? And so I'll put a copy of this on Blackboard so that you can, again, practice with the game ball. Print this off. You can use it in all of your homework. This is all the information that I'm giving you. Also, I'm giving you just 3 significant figures for all of the masses because I don't want you to try to put in 5 or 6 and screw up the calculator. Just, this will get you close enough to be able to circle the right letter, okay, in terms of the exams. So what is it on this? It's a pretty busy table. Up at the top, I have constants and conversions that you can use. Like on here, probably the one that's going to be most useful for you is like pounds to grams. There'll be occasions when you use, what else would you use on here? The gas constant, 8.3 joules per mole Kelvin. Yeah, maybe you'll use the speed of light on a couple of problems, just depending upon where we are in the semester. So you've got constants and conversions. These are for all of my classes, so it even works for PChem. So that's where some of those other constants are. So just don't be bothered by all the extra constants that you're not going to use. So there's the constants and conversions part. And then these up in the upper right-hand corner are the nonmetals, and everything else is metals. Hydrogen's kind of weird. It's not a metal, but it's over there on the left because it only has 1 valence electron, and the columns of the periodic table are arranged by valence electrons. And then these down here, this diagonal, are metalloids. They kind of have a foot in both boats. They have some properties of nonmetals and some properties of metals. So that's they're pretty important. So looking at the entry on the periodic table, the top number is the atomic number, and that's the number of protons. Okay, the bottom number is the average mass on Earth. So this is our natural abundance. That sounds really weird, but that's the truth. Okay. So like 35.5. You won't find a single carbon or a single chlorine atom in the universe that weighs 35.5 grams per mole. What we have on Earth is a mixture of two isotopes. We're going to talk about isotopes here in a second. There's some that have 37 particles in the nucleus and some that have 35 particles in the nucleus. And it's about a 75-25 ratio on Earth. So it's 75% chlorine 35 with 35 particles in the nucleus, and 25% that have 37. When you add those together, the average mass of a scoop of chlorine off of our Earth is 35.5. So that's where these numbers come from. Those are the natural abundance masses. Now that's how we would tell if an asteroid is from some other off Earth, right? So we get it into a mass spec and we test it, and if it doesn't have the natural abundance ratios, then we've got something that didn't start here on Earth. It's pretty cool. Now we can write out these particular, I talked about isotopes. So if we write out, say, carbon 12, the 12 is the number of particles in the nucleus. We call them nucleons. It's protons plus neutrons. And then the 6 is the atomic number. It's the number of protons. A lot of times the 6 is eliminated because if I have a C, I know there's a 6. The C and the 6 always go together. You can have different number of neutrons in the nucleus because they're not charged. They don't change the properties of the element at all. Okay. So you can have carbon 12, you can have carbon 13, carbon 14, so on. So those are the different isotopes. And then you have the symbol. So the symbol and atomic number are so closely tied to each other that you often see the atomic number eliminated. But it's in the periodic table. So up there in the top, like helium 2 is the protons, and then 4 is the mass of that helium. And it's at least on the smaller elements, that's the number of particles in the nucleus. They all weigh 1 atomic unit. And so helium 2, or helium has 4 particles, so it'd be helium 4, has 2 protons, 2 neutrons. And you see the 2 up there shows you how many protons.
Is that just used for like shorthand?
Yes, and so whenever we're talking about isotopes, we need to have that number. If we just write carbon, that's not a problem. We got natural carbon.
When you flip the atomic number and mass number.
Oh, up on the periodic table?
Yeah.
Yeah.
So now it's written on the periodic.
Yeah, it's written kind of backwards on the periodic table. That's a good observation. Yeah. So the mass is proportional to the number of particles in the nucleus. And that's also why that top number is called the mass number, because it's tied very directly to the mass. So here's just a table showing you the different isotopes for carbon. So you could have carbon 11 or 12 or 13 or 14. They all have 6 protons because they're all carbon. They have 6 electrons if they're neutral. So there's a balance in charge. And then here's the different number of neutrons. So if I were to take this 11 and subtract the 6, that's how many neutrons I have. Okay. So there's 11 nucleons in the carbon 11. There's always 6 protons if it's carbon. And so I have 5 neutrons in a carbon 11. Carbon 11 has become one of the most important elements for medical imaging, okay, because it's what emits a positron and becomes a boron nucleus. So positron emission tomography, a PET scan, uses carbon 11. Okay. Carbon is great because you can make sugar out of it. And so they'll feed a person sugar that has carbon 11 in it, and cancer cells are just voracious eaters because they're growing and dividing and growing and dividing. So all of that radio-labeled sugar goes wherever the tumor is, and then the carbon 11 decays into a boron, spits out a positron, it combines with an electron and spits out 2 gamma rays, and we detect that. And that's what a PET scan does. So we're using antimatter in people's brains to detect cancer. It's crazy. Yeah. More about that in PChem. Okay. Now, I want you to really focus on when we use this word or this prefix iso. So iso means same, and so like an isotope, you think that tope is just a little twisted version of the word type. So it's the same type of element. Isotope means same type of element. It means they have the same number of protons. So you could say that they're isoprotonic. That would be another way to say it. But isotope is a little easier. You could also have isoelectronic. So if they have the same number of electrons, they're isoelectronic. So if we were to take chlorine and make it an anion and give it an extra electron, it'd be Cl minus. So the chloride ion is isoelectronic with argon, has the same number of electrons as argon. So Cl minus and argon have the same number of electrons, so they're isoelectronic. So this is a really important prefix that we put on lots of things. It just means the same. Okay, isoneutronic means the same number of neutrons. You could do this all day long, you know. Even in the weather map, see those lines on the weather map? Those are called isobars. Isobaric, that's the same pressure. So you walk along that line on the isobar map, and it's the same pressure along all those lines. Okay, so we've covered the bulk of the material that I think will prep you for getting started on Alex for chapter 2. So now I'm opening it up to your questions. Please, 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 yeah, ask your questions. Yes.
On the Monday's homework,
Mm-hmm.
there's a module called thermochemistry.
I shouldn't have turned that one on. Did I turn that one on? Yeah.
It's there, but it's locked. So.
Okay. It's huh. Really. Shoot me an email to check on that because I don't know. I don't know why that's turned on. Thermochemistry is chapter 5, and so I want to look and see why that's coming up. Yeah, because I didn't intentionally turn it on. So, yeah, thanks. Okay. All right. What other questions do you have? And this again, when you're doing the work, I really depend upon you using that composition book so that you can bring your questions to class too. You can like have the math there, and you can even bring it up. Maybe I could quickly type it in, and we can answer your question on the video. Yes.
Can you go back to slide
7? Okay. This one? Okay. This one here? This one? Okay. Oh, you're just writing down the okay, very good. Filling in the things. Okay. Yeah, so I'm going to depend on your questions and answers. So whenever you're doing the work in Alex, I mean, that's really where you're learning the material. And so write your questions in the margins of your book and bring them to class, because I guarantee you're not the only one with that question. And so we're going to find, that's what the value of this sort of communal time together is, when we really say, I had this question, and it's okay to say, yeah, I had the same thing. We'll really get a feel for where people are in the course material. Okay. Yes.
There was from chapter 1. I know
Yes.
it's already passed, but there was one I kind of got lucky on.
Okay.
that passed.
Yeah, it's great. Okay.
But I kind of want to go back because I know
Yeah.
I didn't get it.
Yeah.
So, I'll be able to go back, or is that not possible?
That's an open question for me right now. I think you should be able to go back and review. There will be a review assignment that pops up after next week when we're getting ready for the first exam. You'll have a knowledge check that takes into account chapter 1 and 2. So you'll probably get some of those questions again. But if you could find it and like the blue titles here, those blue titles on the Alex problems are what I see in terms of picking the modules. Okay, so if you were able to say counting sig figs with measurements are multiplied or divided, if you had a question on that module, then I could go right to that module and I could look to see which ones you're talking about. Yes.
If you want to review, whenever you're on it has a problem for you, click the 3 lines and there's a little tab that says review and he'll bring you back to all the old ones.
Oh, good. Okay. And I think that's what they call open pie time or something like that, where you can just work on, shoring up anything that you might be weak on. You can also get ahead of the course too. So as soon as you finish a module, the next module opens. And I can see there's a few people that have certainly had like maybe AP chemistry or something because they're like burning through doing a speed run. So, which is fine. Just if you get too far ahead of us, don't get complacent because the first test is only on chapters 1 and 2. And so, you're filling your head with 3 and 4, and then you don't want to make a careless mistake on chapters 1 and 2 when we have that test. But I don't see that happening. You'll go through the knowledge check on 1 and 2, and you'll be prepared again. So I see y'all grabbing your books and bags, and it seems like you're ready to leave. But please bring your questions, because I depend upon you. This is your time, and so bring your questions next time. Talk to you later.